Introduction. Hey Ria, what are you doing?
I am doing sentences.
Okay. Do you know in mathematics the sentences are also known as statements?
No, but how we can call them statements?
Would you like to learn more of it?
Yes, Father.
In this lesson, you will learn the reasoning in mathematics. Objectives. At the end of this lesson, you will be able to differentiate between inductive and deductive reasoning, state the statement, form new statements from the old, work with implications, validate statements. Statements. Reasoning is the process of arriving at conclusions from evidence. There are two kinds of reasoning in mathematics. 1. Inductive. 2. Deductive. Inductive reasoning is reasoning from particular facts to general principles. Example: she has red hair, therefore, she has a temper. Deductive reasoning is the reasoning in which the truth of the input propositions logically guarantees the truth of the output proposition, provided that no mistake has been made in the reasoning. Example: a reasoned who infer from the belief. 1. If the room is dark, then either the light switch is turned off or the bulb has burned out. 2. The room is dark. 3. The light switch is not turned off. To the conclusion, the bulb has burned out. Statements. Consider the following two sentences. India has the first Sikh Prime Minister, Dr. Manmohan Singh. The weight of a baby is less than the mother's weight. We can immediately say that the above sentences are correct and there is no confusion regarding them. Consider the sentence, 3 plus 7 makes 11. This sentence is false. Consider one more sentence. Men are more intelligent than women. Some people think that it is true, while some think that it is false. Now we define a mathematical statement. A sentence is called a mathematical statement if it is either true or false, but not both. The statements are often denoted by small letters of the alphabet, P, Q, R, etc. Thus, the statement "Sun is very hot" is denoted as P, sun is very hot. Some important points. The sentences with grammatical situations and the ordered statement are not considered as statements. The sentences in which variable time is used, like yesterday, today, tomorrow, are not considered as statements. Example: state whether the following sentences are statements or not. Give reasons for your answer. 10 is less than 5. Venus is a planet. Mathematics is a difficult subject. Solution: the sentence is false as 10 is greater than 5. Hence, the sentence is a statement. The sentence "Venus is a planet" is a correct sentence as it has been scientifically established. Hence, the sentence is a statement. The sentence is a subjective one as the opinion may vary from person to person. Hence, the statement is not always true or always false. Hence, the sentence is not a statement. New statements from old. Negation of a statement. Let P be any statement. Then the statement expressing denial of P is called negation of P. Negation of P is formed by writing "it is false" before P. Negation is formed by inserting the word "not P." Negation of statement P is denoted as "not P." For example, let P be the statement "Ram is intelligent." Then "not P" is the statement "Ram is not intelligent," or "it is false that Ram is intelligent." Compound statements. A compound statement is a statement which is made up of two or more statements. Each of these statements is called a component statement. By the use of connective words like and, or, we can combine two statements to form a compound statement. For example, P is a statement that there is something wrong with the marking or with the totaling. The above statement tells us that there is something wrong in the marking by the examiner, or there is something wrong in the totaling. The given statement can be split up into the following two statements, connected by the word or. Q is a statement that there is something wrong with the marking. R is a statement that there is something wrong with the totaling. Consider the following two statements. P is a statement that 8 is an even number. Q is a statement that 8 is a natural number. These two statements can be combined with the connective and to get a new compound statement. R is a statement that 8 is an even number and a natural number. Example: find the component statements of the following compound statements. The number 3 is prime or it is odd. Chandigarh is the capital of Haryana and Punjab. Solution: given the number 3 is prime or it is odd, its component statements are: P is a statement that the number 3 is prime. Q is a statement that number 3 is odd. P and Q are connected by or. Chandigarh is the capital of Haryana and Punjab. Its component statements are: P is a statement that Chandigarh is the capital of Haryana. Q is a statement that Chandigarh is the capital of Punjab. P and Q are connected by and. Special words, phrases. The word and. 1. The compound statement involving and is true if all its component statements are true. 2. The compound statement involving and is false if any of the component statements is false. Others may be true. Let P and Q be the component statements, then P and Q is denoted by P and Q. The truth table for P and Q is represented as: for P true and Q true, the P and Q is true. For P true and Q false, the P and Q is false. For P false and Q true, the P and Q is false. For P false and Q false, the P and Q is false. For example, P is a statement that 30 is divisible by 2, 5 and 6. It has following component statement. Q is a statement that 30 is divisible by 2. R is a statement that 30 is divisible by 5. S is a statement that 30 is divisible by 6. Q, R and S are true statement. Also, P is a true statement. The word or. Exclusive or. In a compound statement, P or Q, if exactly one of the two alternatives occur, that is component statements P or Q, but not both occur, then connecting word or is called exclusive or. For example, P is a statement that a cold coffee or a cold drink is available free with a double pizza. This means that a person who does not want cold coffee with a double pizza can take a cold drink in its place. Or if one does not want a cold drink with a double pizza, can have a cold coffee. But a person cannot have both with a double pizza. This is called exclusive use of word or. Inclusive or. In a compound statement P or Q, if at least one of the two alternatives occur, that is, component statements P or Q or both occur, then the connecting word or is called inclusive or. For example, Q is a statement that a student who has taken business studies or mathematics at +2 stage can apply for BCom pass course. Statement Q implies that the students who have taken both business studies and mathematics at +2 stage can apply for BCom pass course, as well as students who has taken only one of these subjects can also apply for BCom pass course. This is called inclusive use of word or. 1. A compound statement with or is true when one component statement is true or both the component statements are true. 2. A compound statement with or is false when both the component statements are false. Let P and Q be the component statements, then P or Q is denoted by P or Q. The truth table for P or Q is represented as: for P true and Q true, the P or Q is true. For P true and Q false, the P or Q is true. For P false and Q true, the P or Q is true. For P false and Q false, the P or Q is false. Quantifiers. There are two quantifiers. 1. There exists. 2. For all. For example, P is a statement that there exists a circle whose radius is 1 unit. This means that there is at least one circle whose radius is 1 unit. Example: write the component statement of the following compound statement. 3 divides 6 and 5 plus 8 is equal to 13. 4 divides 28 and 7 plus 4 is equal to 11. Solution: 1. The given compound statement is 3 divides 6 and 5 plus 8 is equal to 13. The component statements are: P. 3 divides 6. Q. 5 plus 8 is equal to 13. P is true and Q is true. Hence, P and Q is true. 2. The given compound statement is 4 divides 28 and 7 plus 4 is equal to 11. The component statements are: P. 4 divides 28. Q. 7 plus 4 is equal to 11. P is true and Q is true. Hence, P and Q is true. Example: for each of the following statements, determine the inclusive or exclusive or use of words. Give reasons for your answer. The shop is closed if there is a function in the family or it is a closed day. Students can offer Sanskrit or Urdu as a third language. Solution: here the use of word or is inclusive as the shop is closed on a closed day as well as on a day when there is a function in the family. Here the use of word or is exclusive as the student can have both Sanskrit or Urdu as third language but cannot have both of them. Implications. We will discuss the implication of if-then, only if and only if. Two statements connected by the phrase if-then are said to result in a statement called implication. For example, if more mangoes arrive in the market, their prices will go down. If P, then Q is the same as following. If P, then Q means that P implies Q. It is denoted by P implies Q. This says that a number is a multiple of 10 implies that it is a multiple of 5. P is a sufficient condition for Q. For example, knowing that a number is a multiple of 8 is sufficient to conclude that it is a multiple of 4 also. P only if Q. This says that a number is a multiple of 8 only if it is a multiple of 4. Q is a necessary condition for P. This says that when a number is a multiple of 8, it is necessarily a multiple of 4. Negation of Q implies negation of P. This means that when a number is not a multiple of 4, it is not a multiple of 8. Contrapositive and converse. The new statements formed from the given statements by the use of phrase if-then are called contrapositive and converse. For example, the following statement involving if-then. If there is a brisk selling of stocks in the stock market, then the Sensex falls sharply. Contrapositive of statement is, if the Sensex does not fall sharply, then there is no brisk selling of stocks in the stock market. Both the statements convey the same meaning. The converse of a given statement, if P then Q, is if Q then P. Consider a statement. If two integers x and y are such that x greater than y, then x minus y is always a positive integer. The converse of this statement is, if two integers x and y are such that x minus y is always a positive integer, then x greater than y. Use of if and only if. It is represented by the symbol if and only if, which means the following equivalent forms of the two statements P and Q. P if and only if Q. Q if and only if P. P is necessary and sufficient condition for Q and vice versa. P if and only if Q. Example. Write the contrapositive statement of the given statement. If a quadrilateral is regular, then it is a square. Solution. Given. If a quadrilateral is regular, it is a square. Contrapositive statement. If a quadrilateral is a square, then it is a regular quadrilateral. Example. Write the converse statement of the given statement. If a number is divisible by 24, it is divisible by 12. Solution. Given. If a number is divisible by 24, it is divisible by 12. Converse statement. If a number is divisible by 12, then it is divisible by 24. Example. Combine the given statements using if and only if. P is a statement that if a pair of opposite sides of the quadrilateral are parallel and equal, then it is a parallelogram. Q is a statement that if a quadrilateral is a parallelogram, then its one pair of opposite sides is parallel and equal. Solution. Given. P is a statement that if a pair of opposite sides of a quadrilateral are parallel and equal, then it is a parallelogram. Q is a statement that if a quadrilateral is a parallelogram, then its one pair of opposite sides is parallel and equal. Let us combine these statements using if and only if. We get a quadrilateral is a parallelogram if and only if its one pair of opposite sides is parallel and equal. Validating statements. Rule 1. Statements with AND. If P and Q are two statements, then in order to show that the statements P and Q is true, the following steps are needed. Case 1. Show that the statement P is true, and Case 2. Show that the statement Q is true. Rule 2. Statements with OR. If P and Q are mathematical statements, then in order to prove that the statement P or Q is true, we consider the following. Case 1. By assuming that P is false, show that Q must be true. Case 2. By assuming that Q is false, show that P must be true. Rule 3. Statements with if-then. In order to prove the statements if P, then Q, show that any one of the following is true. Case 1. By assuming that P is true, then prove that Q must be true. Case 2. By assuming that Q is false, prove that P is false. Rule 4. Statements with if and only if. In order to prove the statement P if and only if Q, we need to show Case 1. If P is true, then Q is true. Case 2. If Q is true, then P is true. By contradiction. In this, we check statement P is true or not. We assume that P is not true, that is, negation of P is true. Then, we reach at some result which contradicts our assumption. Therefore, we can say that P is true. Did you know? Aristotle made a huge contribution in deductive reasoning. A German mathematician, G.W. Leibniz, has developed the concept of using symbols in deductive reasoning. Summary. Let us summarize what we have learned. Inductive and deductive are two kinds of reasoning in mathematics. Let P be any statement, then the statement expressing denial of P is called negation of P. By the use of connective words like and, or, we can combine two statements to form a compound statement. Let P and Q be the statements if exactly one of the two alternatives occur, that is, component statements P or Q, but not both occur, then connecting word or is called exclusive or. Let P and Q be the statements if at least one of the two alternatives occur, that is, component statements P or Q or both occur, then the connecting word or is called inclusive or. There exists, for all, are the two quantifiers. Two statements connected by the phrase if-then are said to result in a statement called implication. Only if and only if comes under implications. The new statements formed from the given statements by the use of phrase if-then are called contrapositive and converse.